All right. Thank you for joining us today. We are pleased to bring you the webinar called Harnessing the Power of LiDAR-Derived Insights for Economic, Ecological, and Equity-Centered Sustainable Forest Management. Our aim today is to discuss how a LiDAR sensor and DJI Matrice 300 drone are changing the game in forest management. We are going to discuss how CanDrone and our partner Gen4 Services have harnessed this technology to create 3D models and 2D maps, and ultimately save money and protect our forest assets for ecological integrity and our collective social benefit. To start off, we would like to introduce ourselves. CanDrone is Canada's leading consultancy in aerial and ground-based remote sensing solutions. We are a full-service drone agency offering everything from hardware and software, sales, rentals, training, and piloting services to custom drone engineering solutions. We offer drone-based solutions in light detection and ranging, otherwise known as LiDAR, and have used it in industries such as forestry, mining, and construction since 2015. I'm Ian Perry, Solutions Specialist at CanDrone.
And hi, I'm Camille Gay. I'm the Solutions Technician here at CanDrone, and I'm going to show you the data outputs from our forest analysis today.
All right, now we'd like to pass it over to Gen4 Services to introduce their company. Go ahead.
Thank you, Ian. Hello, my name is Stephen Generous, and I am the General Manager and owner of Gen4 Services. Gen4 has been providing multi-phase forest management services to the British Columbia coast since 2008. At Gen4, our main objective is to supply our clients with quality, cost-effective, and innovative resource management options to meet their project objectives. Our new RPAS division under GenDrone is allowing our team to collect data in a manner that is quicker, safer, and more cost-effective than traditional methods of ground proofing and helicopter access. Our team of GIS experts is then able to process and analyze the data captured to provide our forestry professionals with timely, detailed information to support our engineering, silviculture, and forest management planning work. I would also like to say, over the past year, we have enjoyed working with the CanDrone team as our program has developed, and they have provided excellent customer support in all aspects of sales, flight training, data processing, and troubleshooting. And we have been fortunate enough to have several on-site training sessions, which have been immensely productive, informational, and entertaining. Over to you, Patty.
And I'm Patty McKenna. I'm the Senior GIS Analyst for Gen4, and I process most of the LiDAR data.
Hi, I'm Jeremy Erickson, Drone Pilot and Forest Technologist at Gen4 Services.
All right, thank you, Gen4, for those introductions. With a look at today's agenda, we are going to showcase LiDAR in a forest area in the beautiful Cowichan Valley in south central Vancouver Island, British Columbia. We will discuss LiDAR technology and software and how they relate to three aims of sustainable forest management, which include ecological, sociocultural, and economic considerations for managing forests. Ecological considerations consist of conservation goals like protecting threatened and endangered species and their habitats. Sociocultural considerations include human benefits from healthy forests, such as resilience to climate change and the enjoyment of old-growth forest communities. Economic considerations include harvesting timber for creating forest products and sustaining jobs. For the next 25 minutes, we will take you through the incredible capabilities of LiDAR technology and exemplify its use in multi-pronged forest management. Please make sure to input your questions into the question box as we move along, and we will address as many as we can at the end of the presentation. Those which we do not get to on the webinar, we will follow up with email. Now I will pass it over to Camille to overview our technology.
So thanks so much, Ian. So to collect this data set, we use DJI's Matrice 300 RTK drone with Green Valley International's LiRV LiDAR sensor. There are also a few other great entry-level LiDAR sensors on the market that are capable of acquiring the same data. One being the DJI L1 LiDAR sensor, which has the same Avia Livebox sensor as the V70. For this analysis, we also used a software called LiDAR 360 to process our data set. And specifically, we used LiDAR 360's forestry module to create our LiDAR-based individual tree analysis. We really want to focus on digging deeper into the insight that we can derive from LiDAR in the context of forestry. So we did our last webinar on discussing the basics of using LiDAR 360 software. So please find that webinar on our YouTube channel entitled LiDAR 360 Data Processing in 60 Minutes, if you'd like to get started with the basics. So within the software, the forestry module allows you to produce forest inventory data from your point clouds, and some of the main derivatives from your UAV LiDAR point cloud include a ground classification, a DEM, DSM, and CHM. And these terms I will be explaining a little bit further in a few minutes, as well as a segmentation algorithm for individual tree segmentation. So to help you understand how this technology is put to work in our first aim of forest management, the ecological considerations, Ian is going to give us a little bit of a background.
Okay, thank you, Camille. Ecological forest management considers the importance of forest lands as habitat for numerous species. In British Columbia, many streams are salmon-bearing part of the year, and it is important to leave stream corridors undisturbed during timber harvest operations to avoid jeopardizing fish habitat and water quality. This means planning forest access roads around stream corridors with detailed information about the forest floor. A traditional ground-based survey for mapping forest topography is a time-consuming process with hundreds of survey points needing to be acquired on foot. But in contrast, LiDAR mounted on the belly of a drone can penetrate the overstory canopy and scan the forest floor from 60 to 80 meters up at a speed of about 4 meters per second. Using the forestry module in LiDAR 360 software allows us to then filter the ground surface out of the scan and create what's called a bare earth model. These models can be used to make maps of the forest floor in a GIS like ArcGIS or QGIS. This approach saves a lot of time in terrain mapping, allowing us to quickly identify and avoid ecologically sensitive areas like streams when creating forest roads. So Patty, with Generous Forest Services, is going to briefly describe why topography is important to plan harvest activities.
Thanks, Dan. Bare earth hillshades and slope maps derived from the LiDAR are very important components for our project data. Our engineers and GIS professionals use bare earth models to visually analyze the topography, assessing existing road and creek locations. We use the bare earth models in conjunction with slope and contour maps to identify steep areas and terrain features such as rock outcrops and potentially unstable areas. There are both production and safety benefits to the use of these derivatives, including reduced time spent walking in the field in sometimes steep and unstable terrain and adverse conditions. Capturing LiDAR using our RPAS gives us the flexibility to process the point clouds to create DEM, DSM, and the hillshade layers that Ken mentioned, as well as contours and other deliverables at different resolutions and different scales to meet the needs of our individual clients.
Okay, thank you very much, Patty. Next, Camille is going to discuss how we create a bare earth model in LiDAR 360.
Thanks, Ian. So to begin, we're going to discuss the exact steps we took in LiDAR 360's forestry module to create that bare earth model, or digital elevation model, as some people refer to it, so a DEM. So we brought in our 4 flights of UAV LiDAR data into LiDAR 360, which covers about 57 hectares. And then we merged all the data sets together. Then we removed outliers, classified ground points, which then allowed us to create a bare earth model. The bare earth model uses basically this raster interpolation method to fit a continuous surface through all our ground points. And so by stripping away the trees we are able to locate the streams and riparian zones in the area. So as you can see here on the top is the DEM, which gives elevation information, which we can use to then create, to delineate a detailed slope and aspect map that allows us to then map streams and create a stream buffer. These are all really great baseline maps to help us understand how steep the terrain is and where more detailed engineering work might be needed. So yeah, this detailed spatial information can then just be used to help inform waterway protection during future road work and harvesting planning work. So next, Ian is going to transition us to the next aim of forest management, the socio-cultural considerations.
Thanks. Sociocultural considerations in forestry management consider the non-material valuation of forests, and this includes protecting the spiritual, recreational, and aesthetic value of forest lands for visitors and residents to enjoy. Veteran trees are part of the enjoyment value in the Cowichan Valley. Veteran trees are mature trees that exhibit size characteristics that are more important to wildlife habitat and biodiversity. To forest users such as people hiking, walking dogs, or viewing wildlife, these uniquely large trees bring a sense of awe and appreciation for forests and the natural world more broadly. This increases forest enjoyment and improves a forest's sociocultural value. So to encourage the growth of species like cedar and hemlock so that large veteran trees emerge over time, forest thinning is often necessary to provide better growing conditions. This means removing some trees from an overgrown forest so that remaining ones can capitalize on additional light and nutrients for growing bigger and eventually becoming veteran trees. Identifying where candidate veteran trees are and how much thinning is required around them can take hours of ground-based field work. So Patty, can you tell us how you scout veteran tree locations with traditional methodology?
Sure, Anne. Historically, we've used the provincial forest inventory data to locate areas where large trees will likely be found based on the age and height attributes for a particular homogeneous polygon. However, our provincial forest inventory database has many limitations, including accuracy, coverage, and age of data. Only through visiting stands and walking through or assessing a stand by helicopter to get an aerial view will we be able to identify these large trees with any confidence.
All right, thanks, Patty. Now, and plan forest thinning around them in LiDAR 360.
Thanks, Ian. So mapping out our forest tree heights. By doing this, we can see the distribution of tree height and specifically pinpoint where these veteran trees are in the landscape. So we use LiDAR 360's forestry module to derive a DSM, which is a digital surface model, which is a model that includes all the highs and lows as if there was a blanket draped over the surface, including all of the trees in the model. And then we made a CHM, a canopy height model, which is created from subtracting that DSM raster elevation from that bare earth model elevation values. Then we used the CHM segmentation tool, which uses the CHM raster to delineate the tree top center and each individual tree crown, shape, and size. The segmentation tool result includes a few different outputs, including a segmented point cloud where each tree point is assigned to a tree ID. Secondly, a shapefile including a polygon for each tree crown area. And lastly, a CSV file with the resulting tree attributes, which include tree height, tree crown width, tree crown area, and tree crown volume. And then there's also a tree location and a tree ID number. So on the top left is the resulting tree segmentation, where all the LiDAR measurements belonging to a unique tree are assigned to a tree ID number. Then from our CSV file from tree heights, as an attribute, we have a tree height for each tree, and we can then select out our veteran trees, which are 35 to 45 meters tall. These veteran trees are depicted on the top right. And so to help you understand how LiDAR is put to work for our third aim of forest management, the economic considerations, Ian is going to give us a bit of background on harvesting systems.
All right, thanks very much. Harvesting timber provides economic opportunity. The selective harvest system is one forest management approach that allows us to regularly generate income while also letting the forest regenerate naturally. Essentially, we first harvest some mature trees to provide an income while also allowing more sunlight to encourage seedling growth on the forest floor. We remove more mature trees, the bigger the younger ones get, until eventually all the mature trees are harvested and the new generation can take their place and the cycle repeats. Before the initial cut can take place though, a timber reconnaissance must be undertaken to determine where the mature trees for harvest are. Forestry professionals take tree height, diameter measurements, record forest health, and quality factors to establish the monetary value of the merchantable trees. Using LiDAR to create a digital model of the forest and extract tree metrics like height, volume, and crown diameter saves the forester tremendous time. Jeremy, can you describe what's involved in a traditional reconnaissance mission?
For the example we are using for this presentation, ground-based reconnaissance without access to LiDAR data would require us to walk through the timbered 31 hectares on the 57-hectare property to determine where the merchantable timber is located. With access to LiDAR, we can identify where the desired timber is located and assess the terrain from the office, which allows us to focus our field activities on the timber profiles our clients are seeking. We can also clearly see the distribution of younger plantation trees and existing road systems.
All right, thanks, Jeremy. I'd like to pass it on to Camille to talk about extracting forest metrics from the LiDAR point cloud.
Awesome. So to manage the thinning treatment for this forest stand, the goal was to select 15% of trees that are suitable for thinning. So the aim was also to make sure that we were selecting the right trees. We want to make sure we weren't just clear cutting one area. We wanted to select trees evenly across the site to allow for larger trees to continue to grow, like Ian was mentioning, but also to keep the ecosystem intact. So to do this, we chose trees ranging from 25 to 30 meters tall. And to visualize this thinning on the map, at the top you can see the entire forest by tree height, ranging from 1.3 meters to the tallest tree being 48.7 meters. And then on the bottom left, this map is showcasing the trees selected for harvest to thin for the forest structure. And then on the bottom right, you can see the distribution of trees after the thinning has occurred. So as you can see here, 15% of the trees equates to just over 1,000 trees selected for harvest. The factors that inform tree thinning are multifaceted and unique to each forest stand. So to give some more insight into the rationale that informs Gen4's process, Patty, will you explain some of the factors that you consider prior to beginning harvesting in that area?
We look at the condition of the stand, the current condition of the stand, and then we would look at the terrain and accessibility to the stand for harvest. We would also look at the desired outcomes for the harvest.
Awesome, thanks, Patty. All right, so after running the process of LiDAR tree segmentation, we wanted to use the LiDAR tree height measurements derived from the tree segmentation and compare them against our in-field tree height measurements to assess the accuracy of our LiDAR measurements. So after running a simple linear regression model, we found that the LiDAR-derived measurements compared very closely to our in-field measurements with an R-squared value of 0.66. So the results, of course, are not perfect, but a pretty good fit, considering that we only took 25 in-field tree measurements. So overall, we found that our LiDAR-derived measurements were accurate, and the main consideration affecting tree height measurements is usually because of the delineation between the tree crowns in very dense canopy areas, which is hard to do with a canopy height model. And here is also a map showcasing the LiDAR-derived tree heights, and you can see here those tree crown polygons that I was referring to. And with that, it is also super important to note that the tree segmentation is really only just an estimate of the forest composition. The CHM segmentation tool is using a CHM raster to delineate tree crowns. So of course, if there are any tree crowns that are being covered by taller trees, these will not be counted in our tree segmentation. But also another source of error in gathering tree height measurements can come from the in-field measurements. So manually measuring tree height with a hypsometer can actually be kind of difficult, especially on sloping terrain with dense forest canopies. In contrast, LiDAR is able to penetrate through any gaps in the canopy and measure the terrain of the canopy floor, and then the UAV-based LiDAR sensor that we used achieved an incredible point density of 500 points per meter squared. So it's actually quite easily able to also get a measurement from the top of the tree. So with that, the main inaccuracy that you would see in any tree height measurement is a product of the LiDAR system's overall accuracy, which in this case was about 14 centimeters. So then we wanted to take this analysis even further. So we used our in-field measurements and LiDAR-derived tree metrics to create a multiple linear regression model to try to predict DBH, which is diameter at breast height, of each individual tree seen in our LiDAR point cloud. So tree height and crown area were selected as our best correlated DBH predictors. And after creating the model, it was applied to our whole tree segmentation shapefile with each tree polygon. And the model results were as such, where with two of our predictor variables, crown area and tree height, the model adjusted our squared value was 0.6, and both of our predictor variables were significant in the model. So we then used DBH values to calculate timber volume. And so you can see the map seen on the right showing the resulting distribution of timber volume by individual tree. And the total stem volume from our entire 57 hectare site equates to approximately 13 thousand cubic meters of timber. So of course, in the model for each tree, the results are really just a rough estimate. On the left here, you will see a map of tree density showing about 20 to 150 stems per hectare ranging across our site. And these maps of tree height, stems per hectare, and volume distribution all are super helpful for our forest manager Gen4 to get a very detailed picture of what's available in the forest, allowing them to really just have a better plan for operations for generating their income plan. Yeah, so that's kind of our final map there. I don't know if Gen4, if you guys want to add anything. If not, we'll just show our last 3D visualization.
Well, I can just add that, the maps showing the thinning and the removal of volume and density allow us to see the potential impact that the selective harvesting would have on the stand, both aesthetically and with regard to stand structure. And that allows for more thoughtful decision making when it comes time for harvesting or for retention.
Yes, awesome. Thanks so much, Patty. And just here, lastly, we want to show that the goal after predicting tree diameter and calculating volume was to select that 15% of trees that we would slate for selective harvesting. So in this visualization, you can see what the forest looked like before thinning on the left, and then what it looks like after the thinning treatment has taken place on the right. So I guess I can try to play those again if you want to see in real time. So this thinning treatment takes place, and you can make sure that all forest land stakeholders are on the same page about the quantity and location of trees being selected for removal by, being able to show it in 3D before it even happens and make it a more of a dialogue conversation for your forest stakeholders.
Well, that is truly amazing. Thank you so much, Camille. To summarize, we have discussed how a small LiDAR sensor on a drone and the LiDAR 360 processing software suite can be applied in forest management, and specifically sustainable forest management that considers ecological, sociocultural, and economic aims. We have given you the basic overview of the capabilities of LiDAR and LiDAR 360. We have demonstrated the use of bare earth models, or DEMs, and discussed how they help map sensitive habitats on the forest floor. We have shown you the canopy height model segmentation tool and discussed how it can be used to locate the bigger trees so we can nurture them into the veteran trees, the giants that make for old growth down the road. And finally, we have shown you how the tree metrics, diameter at breast height and crown area, can be used to predict all kinds of other metrics in the forest. Just a small number of measurements can be applied across very large areas, saving a great deal of time. So this technology has made major breakthroughs in the forestry sector, and we have shown you a mere sliver of its capability in this short talk. We hope you are inspired to use LiDAR in your forest management, no matter what your management outcomes are. CanDrone and Generous Forest Services are here to provide the tools and expertise for your forest projects. Remember, CanDrone can provide you with the right LiDAR package to buy or rent. We can show you how to use the equipment and provide ongoing support. We host webinars on a monthly basis. Please stay tuned to our social media pages to keep up to date. We thank you very much for joining us this morning, and we will take some questions from the chat box. If we don't get to everyone, remember, we will follow up with an email response. So do leave that information for us.
Thanks, everyone. So I see in our question box, some coming in. What do we have here? Question from Russell: what was the minimum height to classify a veteran tree? For this case study, what was it? We selected 35 to 45 meter tall trees as our veteran trees for the sample. Hopefully that answers that. Let's see, what else do we have here? What was the point density of the LiDAR survey? So it was 500 points per meter squared. That's kind of the base level after, with all the points. We did a ground classification where it basically does a filtering of the points, which we used to make our DEM, and that ground class had about 30 points per meter squared. But overall, the V70 LiDAR sensor gives about 500 points per meter squared. That's all I see on my, oh, here we go. Oh no. Referring to the final model showing the potential outcome prior to harvesting, is this used to do ecosystem integrity evaluations prior to harvest?
Yeah, you certainly could. That's sort of the intent of this presentation, is to show you the tools and a bit of the workflow, and the rest of it comes down to your aims and your creativity and how you use this technology in the full life cycle of any kind of harvest or ecological monitoring or restoration project.
Just a question about subtitles covering the presentation. I think that will be something we can do. Yep, that will be when we upload it to our YouTube channel. The recording will have subtitles.
Here's one for you, Camille. Do you find problems with dense canopies and not being able to get canopy penetration for the ground model?
Yeah, I mean, it's definitely a limitation. Sometimes if it's a really dense forest, you might not get really awesome penetration. The typical LiDAR sort of suggestion would be to fly lower and slower to increase your point density and try as best as possible to see through into the canopy floor. Of course, LiDAR is not, it's not X-ray. So if it's super dense canopy and there's a really thick understory, like you won't be able to get perfect penetration in those areas. So yeah, the best you can do is fly low and slow in those areas. And for this site, there was some areas that were quite dense and we still got a few points through there. We flew at 4 meters per second at a height of 80 or 70 meters. So yeah, it's possible.
Okay, so a question here, does LiDAR data provide any insight about fire fuel in the forest? And I would say absolutely it does. We talk about ladder fuels as being intermediate height vegetation that can grow over time as fire is suppressed in our forests, especially in forests that have a high fire return rate or a high interval. And so we can absolutely scan a forest and we can get a profile with LiDAR 360 and we can see how much canopy exists somewhere between the top of the overstory and the bottom of the forest floor. Generous forests, do you guys have any experiencing managing fuel loading? And how would you envision applying the LiDAR technology?
We don't have any experience yet, but we're definitely moving in those directions. LiDAR is just such an amazing tool and is being used for new forest management techniques on a daily basis. So I see that as being integrated very quickly here with global warming and protecting towns and fire abatement projects that we're working on.
All right. It says, has there been a cost benefit comparison from versus time and cost of drone? So I think Gen4 might have something more to say about this, but I think we're not saying that this is completely replacing any timber cruising. It's just sort of like a really great first step to understand what's available in your forest. And I think Gen4's practice is still that after they've collected LiDAR and done some of their detailed forest analysis on their LiDAR, that they still do go in and do a more thorough timber cruise if needed. I'm not sure if Gen4 has anything to add on that about the cost benefit analysis.
The drone is one of many tools, and LiDAR is an incredible improvement for a planning tool. Starting from day one and using air photos or Google Earth, and there's so much detail you can see in there. You can't see the forest floor, you can't see the quality of the trees, but LiDAR gives you a good indication very quickly for a planning tool where the taller timber is, how spaced it is, what its potential volume is, limitations on the ground, access structures, rock bluffs, all these sorts of things that go into planning from the office that save you time and money and safety on the ground. Getting to a site just to find out that it's in the older days when I first started my career and finding out that there was very limited amount of timber in the area, or there was fish streams that were crisscrossing the block or ecological features, be spending all that time and money to access with a helicopter, a boat, or on ground, and putting yourself in jeopardy for a potential injury is what LiDAR really saves you is that insight of knowing where to go, how to get there, what's the safest route, harvestability options, any sort of limitations. So it's one tool in the toolbox, but it's a big one.
Awesome. Thanks so much, Steve. And just to add to that, I guess one just sort of way to kind of think about it is, you know, we scanned 57 hectares in an afternoon. It was maybe 3 hours. So I don't know exactly how long that might take someone to timber cruise that, but probably longer than 3.5 hours, I would say.
Yeah.
Yeah. Okay.
There's a question here about the difference between broadleaf and coniferous forests and how this technique might be applied in a broadleaf forest community. And so I see it being pretty easy to transfer the.
It's a little trickier, I would say.
Okay.
Just this canopy height segmentation tool that we use does favor conifers. It's finding that treetop center, and it does have a harder time with any deciduous trees. So there's definitely lots of research and papers on using it and having success. Slightly different, maybe tapered models to help with the different structure of the tree. But yeah, this specific canopy height model segmentation algorithm that we used is better for coniferous, but I don't know if that was totally answering the question.
Awesome. Were all the DBH values measured or any inferred from canopy sizes, etc.?
So we measured 25 diameter at breast height measurements and 25 tree height measurements in our total forest. And then we just used those measurements to then make a predictive model, a multiple linear regression model, to then predict every DBH for the whole forest. So in this example, yes, we did predict a lot of the measurements and then did a volume calculation to get stem volume.
Yeah. What's the benefit of using LiDAR over a standard RGB camera? So I can speak to this because it sounds like what we're asking here is what's the benefit of LiDAR over photogrammetry, which photogrammetry uses the passive light from the sun and its reflectance off the Earth's surface. And we build a point cloud using the color imagery, whereas LiDAR is active. So we shoot laser pulses and then collect their returns. So the big difference here is LiDAR is going to penetrate through the canopy and give us a pretty good return of the forest floor. There's a photogrammetry model built with a 20 megapixel camera or a 45 megapixel camera, something like that. It's just not going to give us a very reliable bare earth model. So you could probably do a lot of the tree segmentation, but you're not going to get the digital terrain model. Is that correct? Does that sound?
Yeah, that's pretty accurate. Just photogrammetry has a harder time stitching together a perfect forest compared to LiDAR, where your measurement is 3-dimensional right off the bat. So it doesn't have to figure out, oh, this green leaf is that same green leaf in the other image. And yeah, it just has a direct ability to see the forest structure and get a way better depiction of the DEM.
Right. Here's one. What is the accuracy with aerial LiDAR for determining species, or were we using traditional photo interpretation for species delineation?
What is the accuracy with LiDAR species?
So we weren't.
So we didn't actually determine species from our LiDAR analysis. That's kind of the next step, I guess. But with that, you can't perfectly predict LiDAR or species just with LiDAR data. The infrared laser beam that's pulsing out and getting these measurement returns is able to have this sort of intensity value associated with each return that you're getting. And you will see that you'll get a different intensity value for a couple different types of trees. Mainly you're seeing a different reflective value compared coniferous compared to deciduous trees. So you're able to kind of delineate between those two categories quite easily with LiDAR, but to do any further species sort of analysis, you do need multispectral or hyperspectral data to combine with the LiDAR to predict species. So that's the next step. That'll be in our next webinar. Yeah, we'll do that. Okay.
All right, you said it. Here's one for Generous Forest Services. What would be the ideal frequency of LiDAR data collection for forest management if you were not under financial constraints? So how often would you fly to manage a site typically?
Really depends on the client needs, what's changed in the stand. If we're looking at a client that's looking for details on their road systems that have changed from previously, or maybe some sort of environmental change in the area, they may want a higher frequency. But for the most part, most clients on forest management are looking around 5 years from an overview flight, and more detailed flights maybe every couple of years, but it really depends on your objectives and what you're trying to achieve or an information you're trying to derive from it.
Gotcha. Here's another good one for Generous Forest Services. Is LiDAR the best option for determining best location for road development? How well does it determine potential drainage issues compared with your traditional means?
The LiDAR will spot where the benches are best places to construct roads, best potential crossings of rivers or creeks or other sorts of things like that. So they'll give you a good indication. It comes down to the planner to use the information from the LiDAR to best come through with what we call a paper plan from the office. And then when we get the crew will still be in the woods, and we'll use that information to quickly come up with a best case scenario for any sort of harvesting or access or potential areas. It saves just an immense amount of time and detail of walking when you can see that there is no creek crossings up above, or there's rock bluffs down below, or it highlights all the water courses, any sort of environmental sort of ideas of previous landslides, road failures, anything from the history of either the environmental changes or previous industrial activities. It helps you to give you a good idea of where to start looking and how to plan for it.
All right. Do we have anything else coming up?
Yes. Can you share the processing workflow to generate a DM using LiDAR 360? In our previous webinar that we did, learn LiDAR 360 in 60 minutes, at the very end of the video, after we do a control point report accuracy assessment, there is gives you the steps on how to make a DEM in LiDAR 360. So check that out.
Okay, just looking at more questions. I think we're just about there.
Did someone say experiencing crackling with the audio? Uh-oh.
That's it.
Okay.
Okay, guys, well, we have had a great time bringing you this webinar this morning, and we're so grateful to you for joining us. With any last minute questions, please do pop them into the chat and we will follow up. Remember to think of CanDrone and Generous Forest Services for all your LiDAR and drone needs, and as well as for your forest management projects. Camille, any parting words of wisdom?
that's everything, I think, from me. Thanks everyone for coming.
Have a wonderful week, everybody.
Bye.